Okay, imagine that we have two water tanks, and as you can see, one is clearly bigger than the other. Both are filled with water up to the same level. Now the question here is, which one do you think experiences more pressure? Down at the bottom, you can see a little red ball. That's our diver. And in both tanks, the diver is sitting at the same depth, about 10 meters below the surface. Now before answering the question of which one of our divers experiences more pressure, here are some things that we do know. We know that both tanks are here on Earth, so the gravity is the same. And we also know that they are both filled with regular water, which we know its density. By now, you might be thinking something like, well, the diver on the right actually has way more water on top of him, so he should be the one that experiences more pressure. Right? Well, actually you would be wrong. Actually, since both divers are exactly at the same depth, they will both experience the exact same pressure. But why? Well, to find out, stick around. Alright, let's think about a simple box sitting on the ground. It looks pretty normal, doesn't it? But what's actually happening where it touches the floor? Just a quick refresher, Newton's second law basically says that if you add up all the forces on something, that will equal its mass times its acceleration. Now, our box is not moving, it's just sitting there. That means it's in balance. Also, note that in this case, acceleration is just gravity. Now that we know its mass and acceleration, we can just go ahead and calculate the force, which would be 98.1 newtons. And that downward force is spread across the bottom of the box. If the box covers exactly 1 square meter, then the pressure is just 98.1 pascals. That's basically what pressure means. Force divided by area. And 1 pascal? That's just 1 newton per square meter. Now let's imagine that we compress this box vertically. Now, you might be thinking something like, well, if the object, in this case the box, became denser, then it should apply more pressure, right? And you would again be wrong. Now, my dear viewer, if you were one of the people that actually thought this, I would encourage you to pause the video and try to reason for yourself why the pressure hasn't changed. But if you understood why the pressure didn't change, you might want to skip to this part of the video. Now the answer is that the pressure didn't change because the force hasn't changed. The mass is still the same, and the acceleration is still the same. It's gravity. And the area hasn't changed either. The area of contact is still the same, 1 square meter. But now imagine that we contract the box horizontally. And as you can see, the force hasn't changed. Force doesn't really care about volume, it just really cares about mass and gravity. But oh wait, the area did change. And since pressure is force divided by area, cutting the area in half doubles the pressure. So it jumps from 98 to 196 pascals. So even though we had the same force, the smaller area led to more pressure. In a fluid at rest, like in an ocean or a lake, the pressure gets higher as you go deeper. That's because there's more water sitting on top of you the further down you go. And all that weight of the water above you puts pressure on you. And since water is nearly
incompressible,
it spreads that pressure evenly in all directions. This means that the pressure increases steadily with depth, regardless of the shape that the container has. But where does this formula actually come from? Let's derive this step by step. First, take a column of water with a cylindrical shape with cross-sectional area A and height h. So we know its volume, it's going to be the area times the height. We also know that mass is density times volume. We know that mass exerts a force due to gravity. And like we previously saw, we know that pressure is just force per unit area. Also notice that the cross-sectional area cancels out. Pressure depends only on depth, not on volume or the shape the container has. But what if the cross-sectional area is not the same everywhere? Let's zoom in on a small element of the fluid and use Newton's law to understand how pressure changes with depth. Now, we will consider a very thin horizontal slab of the fluid. It has an area A and thickness delta C. It is located at depth C below the surface. Since pressure is now a function of depth, then the pressure at the top of the slab is P evaluated at C. And the pressure at the bottom of the slab is P evaluated at C plus delta C. We will apply the idea that when something is at rest, the net force acting on it must be zero. Now here are some assumptions that we're gonna make. Feel free to pause the video and check them out. Now let's identify the forces acting on the slab. The first one is the pressure from the fluid below, which pushes upward. The second one is the pressure from the fluid above, which pushes downward. And the third one is the weight of the slab itself. Given that the slab is in equilibrium, the sum of the forces must be zero. And we will take upward as the positive direction, and therefore, forces pointing downward will enter the equation with a negative sign. Now, I will just simplify the equation. And if you remember a little bit about calculus, and you remember the definition of a derivative, then you will notice that as delta C, which is the thickness of the slab, becomes smaller and smaller, it approximates zero. So the left-hand side of the equation becomes a derivative. And we also have to be a little bit careful with the signs, because if we define C as increasing upward, then as we go deeper, the pressure increases. So pressure decreases as Z increases. To find the pressure at some depth h, we integrate both sides. We assume that the pressure at the surface, which is C equals 0, is P0, and we want the pressure at C equals minus h. And there you have it, the hydrostatic pressure formula. So as we were saying, pressure increases linearly with depth, depending only on the fluid's density and gravity. You might be thinking, okay, this is interesting, but is it really that useful? And that's a fair question, but understanding hydrostatic pressure turns out to be far more important than it first appears. Because this simple result, that pressure depends only on depth, density, and gravity, is exactly what leads us to one of the most powerful ideas in fluid mechanics: Pascal's principle. Imagine a fluid confined in a tank with a piston resting on top. Initially, the pressure at the surface is just the atmospheric pressure, and as we go deeper, the pressure naturally increases. We already know this equation. The pressure at any given depth is the atmospheric pressure plus the hydrostatic pressure. Now what happens if we push the piston down, applying an extra external pressure? Let's call this extra external pressure delta P. The pressure at the surface immediately increases by this exact amount. But here's the interesting part. Because the fluid is
incompressible,
this new pressure doesn't just stay at the top. It travels. Pascal's principle states that this change in pressure is transmitted undiminished throughout the entire fluid. So if we measure the new pressure at any depth, the difference between the new pressure and the old pressure will always be the exact delta P. The increase is perfectly uniform. So, how do we use this to our advantage? Welcome to the hydraulic lift. Notice how our second piston, A2, is much larger than our first piston, A1. If we apply a downward force, let's call it F1, on the small piston, it generates a specific pressure in the fluid. By Pascal's principle, this exact same pressure is instantly transmitted to the larger piston on the other side. But because that pressure is pushing against a much larger area, it produces a massive upward force, F2. Mathematically, since the pressures are equal, we can combine our equations. When we solve for F2, we see that our input force is multiplied by the ratio of the areas. A bigger area gave us a bigger force. It kind of feels like cheating, doesn't it? But the universe doesn't work like that. There is a catch. We have to sacrifice distance. To push the heavy load up just a tiny bit, we have to push the small piston down a very long way. This happens because the total volume of the fluid displaced must be identical on both sides. Volume 1 equals volume 2. And since volume is just area times distance, if we solve for our output distance, we see it's multiplied by the inverse ratio. And there it is, the golden rule of hydraulics. What we gain in force, we pay for in distance. A small piston lifting a massive car. The crushing weight of the deep ocean. They might seem like entirely different phenomena, but they are bound by the exact same truth. Pascal showed us that fluids don't care about raw power. We can simply trade distance for force. And the ocean teaches us that sheer volume is an illusion. Only depth truly matters. The universe is constantly balancing these invisible scales, stripping away our human intuition and leaving only pure mathematics. You just need the right equations to see it. Thanks for watching. Keep looking beneath the surface, and until next time. And if you enjoyed this video, consider giving it a like and subscribing. It really helps, and I highly appreciate it. So thank you. Also, check out my other stuff.